AI just caught something in an ancient Egyptian quarry that nobody can explain. And the longer you look at the data, the worse the problem gets. Because what the machine found carved into solid granite, stone harder than steel, matches a cutting process that humanity was not supposed to have for another 4,000 years. The marks are still there right now. You can walk up to them. You can run your fingers across the surface. And once you understand what the numbers actually say, the official story stops working completely. This is not a theory posted on some random forum. This is measurement data, geometric analysis, tool classification run against thousands of known cutting signatures, ancient and modern. And the result that came back does not fit any tool that existed in the ancient world. Not even close. Let's start at the place where this all becomes undeniable. The Aswan granite quarries sit in southern Egypt, where the Nile bends through ancient hills and the air carries the kind of dry heat that makes every surface look bleached and permanent. From a distance, the site looks like what it is supposed to be, a massive ancient industrial zone. Scattered boulders, abandoned fragments, channels cut into bedrock, the silence of a place that used to thunder with labor and now just sits quietly in the sun. Tourists walk through it every day. They stand next to the famous unfinished obelisk, a stone monument that would have weighed over 1,000 tons if it had ever been finished. And they take photographs and move on. But if you slow down and look at the walls, something starts to feel wrong. Carved into the granite surfaces, not sandstone, not soft limestone, but granite, one of the hardest natural materials on Earth, rated 7 on the Mohs hardness scale, harder than steel, are smooth curved marks, long flowing arcs, scooped depressions that nest into each other like frozen waves, precise, uniform, repeated over and over across the quarry walls, the quarry floor, the sides of blocks, the vertical faces. The more you look, the more you realize these marks are not random. They are not rough. They have a shape to them that does not feel like it came from a swinging hand. Now here is what mainstream archaeology has been saying for over a century. Ancient Egyptian workers shaped this granite using dolerite stones, hard, dense, fist-sized balls of rock that workers would swing repeatedly against the granite surface, slowly grinding it down through sheer force and persistence. Armies of laborers, hours, days, years of pounding. Heroic effort applied to the hardest stone in ancient Egypt. It is a story that holds together on paper. The problem is what happens when you actually try it. Researchers have run this experiment. Real dolerite stones, skilled workers, controlled conditions. They struck granite the way the textbooks say it was done, thousands of times. The marks they produced were rough and uneven, irregular pits with inconsistent depth. No uniform curvature, no mathematical regularity. They looked exactly like what you would expect from human hands working under difficult conditions, which is to say, they looked nothing like what is on the walls at Aswan. The Aswan marks looked like something else entirely. And then AI looked at them, and that is when this story became something nobody in mainstream Egyptology is comfortable talking about. High-resolution photogrammetric scans of the Aswan quarry surfaces were fed into an AI analytical framework capable of cross-referencing geometric signatures against thousands of known tool profiles. Ancient tools, modern tools, hand tools, machine tools, everything. The system was not given a preferred answer. It was given the stone and asked one simple question. What made this? What came back was not a description. It was a measurement. Every arc radius, every entry angle, every cut depth, every spacing interval across hundreds of individual marks on the quarry surface. The data was precise enough to compare against both ancient and modern cutting methods with high confidence. And the first number that came back from that analysis is the number that changes everything. The variation in cut size across all those marks, the spread between the smallest and largest, the inconsistency from one cut to the next, came in at roughly 4 to 5%. 4 to 5% variance. Stay with that for a second, because that number is the center of everything. When a skilled human craftsman performs a repetitive cutting motion, even with a precision modern hand tool, even someone who does this for a living, the natural variation in their output typically runs between 12 and 22%. The human body drifts, muscles fatigue, the angle shifts slightly with each swing. The depth changes as the arm tires. The spacing becomes irregular as attention wanders. That is not failure. That is biology. No human being is a machine, and the variance in their work reflects that fact at every scale. 4 to 5% is not biology. 4 to 5% is a controlled industrial process. And then there was the angle data. The entry angle of the cutting tool into the granite, measured across hundreds of individual cuts in different locations, different orientations, different depths, spread across an entire ancient quarry complex, varied by less than 2 degrees. Less than 2 degrees of angular drift across an industrial site carved into the hardest available stone. In open spaces, in tight corners, on horizontal surfaces, on vertical walls at the top of the quarry deep in confined shafts, the angle held. consistent, repeatable, indifferent to the working environment. When the AI ran its closest match classification against its modern tool database, it returned 3 analogs: diamond-tipped rotary cutting systems, water-jet cutting equipment operating at tens of thousands of pounds per square inch, ultrasonic cutting tools that vibrate at frequencies beyond human perception. Every single one of those technologies was invented in the 20th century. The closest match on the list, the top result, was industrial-grade rotary cutting using a diamond composite abrasive tip, a powered rotary cutter with industrial diamond abrasive, in a quarry that predates electricity by thousands of years. Read that again. Now let's talk about where some of these marks are located, because this is where the physics stops the official explanation completely. The marks are everywhere in the Aswan quarry. That alone is unusual, but spend enough time looking, and you start to notice that some of those cuts are in places where no human being could have physically stood to make them. Tight interior corners where 2 granite faces meet at angles so narrow that not even a child's fist could swing a dolerite pounder with any meaningful force. Vertical surfaces sealed beneath blocks that were never fully removed, locked away from above while the work was apparently still in progress. The marks are there on those sealed surfaces too, identical in geometry to everything else. Then there are the shafts. Across the quarry complex, geological surveyors have documented deep, narrow pits that plunge 30 to 50 feet below the current surface. Some of these shafts are no more than 3 or 4 feet wide at the mouth. Their walls are smooth, marked with the same curved, arcing patterns found everywhere else in the open quarry above. Think about what it would take to produce those marks by hand. You lower a worker into a pit barely wide enough to turn around in, granite on all 4 sides. No room for a full swing, no meaningful leverage, near total darkness, choking granite dust hanging in air with nowhere to go, heat building with every foot of depth, no ventilation. And somehow, at the bottom, the marks on the walls are geometrically identical to the marks made in the open air above, where a worker would have had full range of motion. The quality does not degrade with depth. The consistency does not waver as conditions get worse. Whatever produced those marks was completely indifferent to the environment it was working in. A dolerite hammer requires a minimum swing arc of roughly 18 to 24 inches to generate enough impact velocity to cut granite at any meaningful rate. The interior diameter of these shafts does not accommodate that arc at the lower depths. It is not marginally tight. It is physically incompatible with the tool the standard explanation requires. When the AI processed the shaft data, tool force required to produce the observed surface texture at granite's hardness level, cut angles relative to available working clearance at multiple depth intervals, it returned a definitive result. The marks in those confined spaces cannot have been produced by any percussive hand tool. The geometry does not permit it. The physics does not support it. Whatever made those marks operated in confined spaces without needing human range of motion. It maintained consistent cutting characteristics regardless of orientation. It applied force directly against the stone surface without depending on a swinging arm behind it. That is not a Bronze Age tool description. That is a powered instrument. But the spatial impossibility, as disturbing as it is actually the second most troubling finding in this analysis. Because when the investigation went microscopic, the evidence became even harder to dismiss. Hammering granite leaves an unmistakable microscopic signature. The crystals in the stone fracture along cleavage planes. The surface is rough at the grain scale, full of angular breaks, stress fractures extending below the visible surface into a subsurface damage zone several millimeters deep. When you pound granite, you destroy it, grain by grain, until what remains approximates the shape you want. Under a microscope, percussive granite work looks like a battlefield, angular, violent, chaotic at the mineral scale. The Aswan marks do not look like that at all. Material scientists who examined high magnification samples from the quarry surfaces described what they found as controlled material removal. The crystal structures at the cut surface are sheared, not fractured. The individual mineral grains at the cut boundary show clean separation, sliced through, not broken. The transition from cut surface to uncut granite is sharp and defined. A clean boundary with no subsurface damage zone radiating inward. It looks less like the aftermath of percussion and more like the surface you get when a precision rotary tool passes across a material at calibrated speed with fixed geometry. And then there are the spiral patterns. Tiny spiral traces visible at high magnification on the cut faces, patterns consistent with the surface left by a rotating tool moving across granite in a controlled arc. These are not random scratches. They are directional. They are consistent in their handedness, rotating the same way across multiple cut surfaces examined in different sections of the quarry. That consistency implies a tool with a fixed rotational direction. Nothing in the ancient hand tool inventory produces a consistent rotational spiral trace. Nothing. Then there is the thermal evidence. Localized zones of thermal alteration are present on the cut surfaces. Microscopic regions where the granite shows evidence of heat exposure that could not have come from simple stone-on-stone friction. When two pieces of granite are rubbed together, friction temperatures distribute broadly across a wide contact area. The thermal signatures in the Aswan cuts do not. They are point source localized, consistent with a small, rapidly rotating contact area, like a rotary tool tip rather than a broad, sliding surface. The temperatures implied are far beyond what dolerite on granite percussion produces under any experimental conditions researchers have been able to replicate. And then the trace material analysis found something that should not be there. Microscopic particles of corundum, crystalline aluminum oxide, rated 9 on the Mohs hardness scale, harder than granite itself, were identified embedded in the cut faces. Corundum is the same material used in modern industrial abrasive wheels. It is a material modern precision cutting depends on. Found inside cuts supposedly made thousands of years before industrial chemistry existed. When the full microscopic data set was processed, the spiral patterns, the thermal signatures, the clean subsurface boundary, the anomalous trace materials, the AI returned the same classification it had returned from the geometric analysis. Industrial-grade rotary cutting with diamond composite abrasive tips at 94% confidence. Not bronze, not dolerite. Diamond composite abrasive in an ancient quarry. Now here is where it gets deeper, because the quarry marks are not all the same age. At several locations in the Aswan complex, ancient red ochre paintings have been found sitting directly on top of the scoop marks. The paintings are resting on the cuts, which means the cuts are older than the paintings. Radiometric dating and analysis of those paintings places them at a minimum of 2,000 years before the earliest dynastic Egyptian civilization. Some estimates push even further back, which means the marks beneath the paintings are older still, pre-dynastic, pre-pharaonic, from a period when, according to the mainstream archaeological record, Egypt was home to tribal cultures with stone tools and no centralized engineering tradition capable of producing anything close to what Aswan shows. And then the temporal analysis returned the result that stopped people in the room. When AI correlated cut geometry against estimated surface age across the full dataset, the output came back with high confidence pointing in a direction nobody expected. The older the cut, the higher the geometric consistency. The newer the cut, the more variable. The rougher, the more human. The oldest cuts are the most perfect. The newest are the most crude. Read that again carefully because it runs backward against everything we know about how civilizations develop. Technology is supposed to improve over time. The earliest work should be the roughest. The most recent should be the most refined. That is the story of every human civilization ever studied. Tools get better. Techniques accumulate. Knowledge compounds. Each generation sharpens what the previous one started. The arrow of progress points forward. At Aswan, it runs the other direction. The later quarry marks, the ones clearly associated with known dynastic Egyptian activity, the ones that postdate the ochre paintings, are rougher, less controlled, more variable. They are consistent with what conventional Bronze Age tools actually produce. The earlier marks are geometrically flawless. The statistical significance of this inversion, when processed across hundreds of cuts at multiple locations across the quarry complex, landed in the top 1%. Not a sampling artifact, not observational bias. A genuine, consistent, reproducible pattern running through the data. The marks beneath the paintings are older than the civilization we credit them to. The civilization that came after made worse ones. That one sentence alone is enough to break the textbook timeline. What does it mean? It means one of exactly two things. And neither of them fits comfortably inside the world archaeology has spent a century building. Either a pre-Egyptian civilization, predating dynastic Egypt by thousands of years, possessed cutting technology more advanced than anything the Egyptians themselves could produce. A civilization that worked these quarries, shaped this stone with a process that has no equivalent anywhere in the known ancient world, and then disappeared before the first pharaoh ever ruled, leaving nothing behind but these marks, too precise to explain, too old to assign to anyone, a people who came, who worked, who produced results that surpass what came after them, and who then vanished so completely that even their name is lost. Or the technology existed at the very dawn of what we call Egyptian civilization, and was subsequently lost, not replaced by better methods, simply gone, allowed to vanish for reasons no historical record captures, leaving later workers to produce inferior results with inferior tools on stone that someone else had shaped with impossible precision before them. The knowledge draining away generation by generation until all that remained was the memory that it had once existed, written into rock too hard for the forgetting to erase. In either case, something was here. It worked, and then it did not work anymore. There is one more layer beneath all of this, and it may be the most quietly unsettling detail in the entire analysis. Granite is not uniform. Beneath its surface, it contains a complex internal architecture, veins of differing mineral composition, zones of weakness and relative hardness, planes where the crystal lattice is more likely to fracture under stress. Mapping those internal structures accurately is difficult, even with modern equipment, ground-penetrating technology, geological surveys, skilled interpretation. It takes time and sophisticated tools to read what is happening inside a granite mass before you ever touch it. The ancient cuts at Aswan follow those internal veins with uncanny precision. The curved marks do not just remove material at random. They track along grain boundaries. They navigate around harder mineral inclusions. They exploit natural planes of weakness in ways that minimize force requirements and maximize material removal efficiency. In engineering terms, the placement is optimal. Not approximately optimal, genuinely, measurably optimal. Modern quarrying operations try to achieve this with sonar scanning and geological modeling. They succeed partially and inconsistently. Modern quarries with modern instruments still waste material by cutting against the grain, still fracture blocks along unintended planes, still lose tonnage to paths that looked right on the surface but ran into harder material beneath. The ancient cuts at Aswan achieve optimal grain following more consistently than modern operations typically manage. When AI mapped cut geometry against estimated subsurface mineral structure using surface mineralogy as a proxy for internal grain architecture, the results returned a statistically significant alignment between where the cuts were placed and where the stone's internal weak points would be expected to lie, at 88% confidence. Whoever made those marks was not just cutting granite. They were reading it, understanding its internal three-dimensional structure before they ever touched it, targeting the precise locations where the stone would yield most efficiently to whatever tool they were using. The cuts are not placed where it was easiest to reach the stone. They are placed where it was easiest for the stone to come apart. Those are two very different things, and the second one requires knowledge, the first does not. Either that represents geological understanding developed over an extraordinarily long period of working this specific quarry, knowledge never recorded, never transmitted, simply vanishing with whoever held it, or it represents some form of subsurface detection capability that has no equivalent anywhere in the Bronze Age archaeological record. They knew where to cut before they cut. They cut there precisely, every time, across hundreds of individual operations, spanning a quarry the size of a city block. Then they stopped, left no manual, no schematic, no record of how they knew, just the marks, optimal, precisely placed, following the stone's own hidden architecture like someone reading a blueprint no one else could see. And then there is the unfinished obelisk itself, the most famous artifact in the entire Aswan complex. Over 1,000 tons of granite, partially shaped and simply left. The standard explanation says a crack in the stone caused the abandonment. The problem is that cutting marks continue past the crack. Work apparently proceeded after the fracture appeared. Whatever ended the project, it was not the crack alone. Look at the marks on the obelisk's surface. They are the same curved patterns found throughout the quarry. Identical geometry, identical variants. At the base, where the cutting would have been most confined, where workers would have been operating in the tightest available space, the marks are no different from the ones made in open air above. The precision does not drop when the space gets smaller. That is exactly what you expect from a powered instrument. It is exactly what you do not expect from a handheld percussive tool that depends on a swinging arm behind it. Someone started this obelisk, someone confident enough in their tools and their process to commit to a project of that scale, the single largest monolith ever attempted in ancient Egypt, something that would have stood taller than any monument the civilization ever completed. Something stopped them before the end. They never came back. They left no record of what stopped them or what they were using. This pattern is not isolated to Aswan. The same precision signature appears at the Valley Temple associated with the second Giza pyramid, one of the oldest surviving Egyptian monuments, built from massive granite casing blocks fitted so tightly that a blade cannot be slipped between the joints. The cut surfaces on those blocks show the same anomalous characteristics seen at Aswan, the same entry angle consistency, the same sub 5% variance, the same clean shear boundary under microscopic examination, rather than the subsurface damage zone that dolerite percussion always leaves behind. The same signature appears at granite sites in the Nile Delta. The same inversion of age to precision. The same mismatch between proposed tools and observed results. Every location where the oldest, most precisely worked granite survives shows the same unexplained characteristics. At every one of those sites, the later work, attributed with confidence to known historical periods, is rougher, more variable, consistent with what conventional Bronze Age tools actually produce. This is not an Aswan quirk. It is geographically distributed across the most ancient monumental construction sites in Egypt, applied consistently, repeatedly, by whatever process or civilization or knowledge system produced it. A tradition or an infrastructure that then ended and left only the marks behind to prove it had ever existed. Here is the honest answer to what all of this means. We do not know. And that is not a comfortable thing to say about a site that professional archaeologists have been studying for more than 150 years. The marks show 4 to 5% variance across hundreds of cuts. Entry angle consistency within 2 degrees across an entire industrial complex. The closest modern process match is industrial rotary cutting, with diamond composite abrasive tips at 94% confidence. The temporal correlation, oldest cuts most precise, newest cuts crudest, is statistically significant at the top of the measurement scale. The spatial analysis of the shaft marks rules out percussive tools on physics grounds, not opinion grounds. The microscopic shear signature matches powered rotary cutting and matches nothing in the Bronze Age toolkit. That is the data, full stop. Every conventional explanation fails when tested against those numbers. The diorite hammer theory, run against the variance figures, produces results that differ from the observed data by a factor of 3 to 5. The spatial constraints of the deep shafts make percussive work physically impossible, not difficult. Impossible. The microscopic evidence points in one direction with a confidence level that would be considered conclusive in any modern forensic context. The temporal inversion has been known in some form for decades. Researchers who spent time at Aswan noticed that the oldest looking marks seemed cleaner, more uniform, harder to explain. They noticed. They moved on. There was no framework available to quantify what they were seeing, and no institutional appetite for where quantifying it would lead. The framework has now been applied, and the answers it returned are the most important unanswered questions in the entire field of ancient history. Think about what it means for a method to be real enough to leave its signature in the hardest stone on Earth, repeated hundreds of times, executed at industrial precision across an entire quarry complex, and then simply walk out of human history without leaving a single tool behind. Think about a civilization, or a knowledge tradition, or whatever it was, that knew how to read granite from the inside and shape it from the outside. That built something designed to stand forever, and then vanished so completely that for thousands of years, the people who came after them, who walked the same ground, who quarried the same stone, who tried to do the same work, could not match what the earlier ones had done. The people who came after them produced inferior results, not equal results, not slightly worse results, measurably, consistently, statistically significantly worse results, as if the knowledge had not evolved or been replaced, as if it had simply been cut out of history all at once and never returned. So here's the question that matters. If the oldest cuts in a quarry are the most precise and the newest are the crudest, what does that tell you about the people who made the oldest ones? Were they Egypt before Egypt? Were they something that existed so far back that even the ancient Egyptians had already lost the memory of them? Or were they something that the official history of human civilization has never had room for? The marks are still in the stone. The stone is still in the quarry. The quarry is still in Egypt, sitting in the heat beside the Nile, waiting for someone to finally write the sentence that the data has been pointing toward for a very long time. Something built this. Something knew how. And then that knowledge was gone, and no one has been able to explain where it went.